Today we're going to talk about a really famous experiment, or very important. It's probably not, I think your ideas of what are famous are different than mine. How about this? A very important experiment in the development of both physics and chemistry. And it's something called the Millikan's oil drop experiment. So Millikan and his compatriots were doing this experiment in the beginning part of the 20th century. It was performed in 1909, not published until 1913, so we're just going to put that there. I think just for a little bit of background about what was known at that point. Remember at the beginning of this unit I said that Franklin et al. Didn't really know what an electron was, right? They just thought there was this electrical fluid flowing from place to place, this positive electrical fluid flowing from place to place. To back it up a little bit, 1899, and I said this in the beginning of this unit, someone named J.J. Thomson finds out that there's this particle, which used to be called a beta ray, that was emanating from a lot of radioactive materials. You probably learned about beta decay from chemistry. They thought the beta ray was a ray, and Thomson actually discovers that this beta ray is the electron, right? That it was an actual particle, not a portion of the electromagnetic spectrum. And so J.J. Thomson discovers the electron in this year, but something about this is that the way he does this, he's not able to actually say anything very specific about the electron other than it's really, really, really small, as well as the electron had a negative charge. And he was able to discover that by the way that the electron reacted to a magnetic field. Now, what he is able to actually find out about the electron is he actually knows the ratio of the electron's charge to the electron's mass. Once again, without knowing the experiment that Thomson does at that time period, we would not be able to, it's hard to explain why he's able to know what this ratio is, but to suffice it to say, he has a really precise number for this quantity. He knows that this is 1.7563 because he knew it's that many significant figures times 10 to the 11th coulombs per kilogram. Okay, so he's got a pretty good idea about that, but he doesn't know enough. But if anyone were able to find either of those two quantities, we would obviously then know the other. Now you should also know about Thomson. He was able to do that. Remember, he puts out his plum pudding model from there, right? The plum pudding model where mass was continuous and the pudding part was the positive bits of mass, and then there were these little negative things studded into them, the electrons. And then during radioactivity, for some reason, these electrons shot out. That was his model. We know that model is wrong. Boom, wrong. Not that Thomson at the time knew that was wrong. It is Rutherford and his gold foil experiment, 1911, where he figures out something about the actual structure of matter, right? Where we figure out the nucleus, 1911. Ernst Rutherford in his gold foil experiment, and I'm not going to go through it because you theoretically have gone through that in chemistry, right? But remember, the nucleus is found, the dense positive center of mass, and something that we're able to see with the nucleus is that matter is mostly empty space. And Rutherford didn't know what to do with the electrons, but he knew that matter was neutral, so he just had the electrons orbiting, right? So he knew something about the charge to mass ratio of them. He didn't really know all that much about the structure of them, but you can see that Rutherford was doing the gold foil experiment. He published this in 1911 at about the same time that Millikan is doing the oil drop experiment. In fact, Millikan and Rutherford are contemporaries of one another, so they were in communication during all of this process, and so there's probably some cross-pollination between their work. But with that being said, let's look at the Millikan oil drop experiment. Now, I'm not going to show you the setup of the oil drop experiment as Millikan did it, because it was pretty complicated compared to what I'm going to show you. I did this experiment, or recreated this experiment in college as part of a lab course that I had to take my junior year, for my physics degree, in which you had to pick a series of classical experiments and recreate them. And so the Millikan oil drop experiment was one of the ones that I chose. So I'm actually going to walk you through the version of the experiment that I did. And if you're interested, you can see what the actual Millikan apparatus looked like. So substantively though, it's the same experiment. So what it takes is, unshockingly, a parallel plate capacitor, since that's what I've been building up to this entire time. The next thing that we have here is that we want to create an electric field here. So what we do is we connect the plates of the parallel plate capacitor to something that we will call a variable voltage source. So here, this box here, variable voltage source. And so essentially it's just a big box that looks like it has a big dimmer switch on it, and I can change the potential difference supplied to the plates. Well, why is that important? Because remember, the magnitude of the electric field in there is the ratio of the potential difference you put between the plates divided by the distance between the plates. So here, this distance here is a set distance, delta S, right? And so by varying this, I can vary the strength of the field. Now, it's called the oil drop experiment for a reason. So what he did was he took a perfume bottle, right? An atomizer. You may have seen these. Some fancy French perfumes still use them, but it was very common back in that day, where you had a little bulb here, right? You squeeze the bulb, and it sort of blows across the top of there, pulling some liquid up and spurting it out in a fine mist, right? So here's my atomizer. All right. Now, my atomizer has an electrical thing near it here. Here's a wire that's connected to another apparatus, another wire down here connected to an apparatus. We won't talk about it exactly, but what's happening here is as the mist is coming through here, there are sparks jumping across this gap. So spark, 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 spark. So those are electrons, and then as the oil droplets go through that, they become charged, and they become charged negatively, right? And they're shot into the field, and they are negative when they do that. So what ends up happening is, because they're oil drops, let's look at any one given oil drop. So here's an oil drop, and that was shot in this direction. So an oil drop actually has mass. That's a silly statement. Actually has significant mass such that the force of gravity would act downwards on it in an appreciable way. And if just the force of gravity were acting on that mass, what would it do? Well, that oil drop then would not just go across here, it would go into projectile motion, right? It would follow a parabolic path downwards like that, right? And strike the plate. So what you do in the Millikan's oil drop experiment is you set up such that, remember, these are negative, the potential difference such that the bottom plate is negative and the top plate is positive. So there's a electric field going in this direction. Remember, these are negative particles, so they would feel an electric force opposite the direction of the field, and so an electric field upwards. It's very important about this orientation of your field, where this is, the top plate has to be at a higher potential than the bottom plate. You got to set up your variable voltage source effectively. So here's the thing. So what we're going to do here is we're going to shoot oil particles in here. And when you do that, you actually shoot several hundreds to thousands of them. And what we noticed, or what you notice when you do this, and this is the first observation, is that some of the oil drops travel in parabolic paths downward, right? With the downwards concavity like we did there, okay? And that always happens, right? Every time you squirt the atomizer, every single time some of the oil drops travel in a parabolic paths downwards. But every time you do it, some of the oil droplets travel in parabolic paths upward. Okay? So in other words, they take this path. Why are they doing that? Well, we'll talk about it. And this always happens. Every single time you squirt this, that always happens. And this always happens as well. Every single time that you squirt the oil droplets, that happens, right? But what happens sometimes, and not every time, we'll talk about what we vary in a minute, right? In certain circumstances, some oil drops travel straight. Okay? So they just go right this way. Okay? So, this is sometimes, not always. So what are we varying here? Well, what we're varying here is, we'll talk about what we could vary, but what we're really varying here is this potential difference, right? By varying the potential difference, we're varying the electric field. And by varying the electric field, we're varying the electric force, right? Because the electric force is going to be equal to Q naught times E. And so what's Q naught there? In this, Q naught has to be the charge that's experienced in the force. So this Q naught is the charge on the oil droplet. Okay? So when this thing gets zapped, the oil droplet has a certain charge. The fact that these always happen, and this sometimes happens, must mean that these oil droplets are not getting identically charged. Because if we're traveling this path, what must be true? Hopefully what you said is that the electric force is greater than the gravitational force. And this is when the electric force is less than the gravitational force. What about this one? This must be when the electric force's magnitude is equal to the gravitational force. Well, let's talk about that gravitational force for a second. Right? So back to a normal color, Fg. Well, what is Fg there? Well, Fg is the mass of the oil drop times little g. Now, here's where the experiment is terrible. You might be saying to yourself, oh my God, mass of the oil drop, how would I know that? Well, what you're actually doing when you do this experiment is the distance here, delta S, is really, really, really tiny. Like it is less than a centimeter. And you're looking into this area using the ocular of a microscope, right? So you squirt the thing and you're looking through this thing. You're looking at all these hundreds, if not thousands of oil droplets and seeing what they do. But here's the thing. In order to remove a variable from the experiment, you have to calibrate your atomizer such that the masses of the oil drops are all identical, or with an experimental error, reasonably so. How on earth do you do that? Well, here's how. I'm using an oil of a particular density, and I know that density. And so density is the mass to volume ratio. So what you're doing when you look through that scope is you first calibrate your equipment such that the volume of these oil drops are identical. And since you're looking through this little ocular, what you're really looking for is that these oil droplets look like little spheres. The volume of a sphere is, of course, 4/3 pi r cubed. You are calibrating the equipment so that you have oil droplets that have the same radius, but you're actually looking at the diameter, and it is maddening. It is absolutely maddening to calibrate this atomizer, because if you don't have equal size oil drops, you can only take data from oil drops of a set diameter for the entire experiment. And you do not hundreds, thousands of trials of this, okay? Right? But the entire time, you can only take data in this cloud of oil particles for ones that have a very specific diameter, because you're never going to get them all to have the same diameter, because that's just unreasonable. So you have to pick the diameter that you're okay taking data with and kind of go from there. It is a maddening experiment. So what are you doing? Well, knowing now that the FG is a constant for the experiment, or at least what you're taking data on, what's not constant is FE, because you are manipulating FE by doing delta V. So here's what happens. Just to go through this a little bit more specifically, the actual observations, the critical observations. What you note when you do this, so what you do is you set the delta V, the voltage, at a specific value, and then you squirt, and then you're looking to see, obviously the ones that we want are the ones that go straight across, yes? But that doesn't always happen. So you start the voltage at a very, very, very specific voltage, whatever it is, and then squirt, oh, nothing goes straight across, damn it. And then you just change the voltage slightly, squirt, oh, nothing happens. In fact, for the vast majority of voltages, no oil droplets travel straight. Okay? Then you get to ones where, oh my God, magically it goes straight across, and then you increase the voltage again, and they stop going straight. None of them are going straight, and then you go again, and then you increase a little bit, nothing, increase a little bit, nothing, increase a little bit, nothing, and then you hit another voltage where they go straight, and then second you're off that voltage, and it's so fiddly, it has to be like exactly a value. If you're just a little above or a little below, nothing goes straight, and then you start to find all these voltages where the oil droplets go straight, and then what you find out is that all the voltages that allow a particle or an oil particle to go straight are all integer multiples of each other. And like I said, you do this hundreds, if not thousands of times, and all these voltages are exactly integer multiples of each other. Because let's look at what's happening there. Fg, so the ones we're concerned with are when the Fg equals the Fe. So it's the mass of the oil droplet times little g is equal to the charge on the oil droplet times the electric field strength at that particular thing. And so what we're calculating then is, remember, this is related to the voltages, so M oil, G is equal to Q oil delta V over delta S. And I'll remind you that we know the value of this, we know the value of this, and we know the value of this. And so we're varying these to get these. So we're solving for the charge on the oil droplets, okay? So what are the conclusions? See if you can guess what the conclusion of the Millikan's oil droplet experiment is. Okay, there are two, because there are two major results. The fact that this equality was only true at specific delta V's must mean that this equality only happens because Q is only occurring in specific values. That familiar? Hopefully it is. Another way to say that only certain voltages worked was, another way of saying that is that the voltages that worked to allow the particles to go straight was quantized. This proved that charge is quantized, only occurs in specific amounts. And the fact that all the voltages are integer multiples of each other meant that there had to be some lowest amount that all of these voltages were a multiple of. And Millikan finds that voltage and finds that all voltages below that value Nothing ever goes straight. So he's able to find what he called the quantum of charge. Quantum is a word just means that the thing that you multiply everything else by in order to see the value, right? And so he's able to determine that that quantum of charge is 1.6 times 10 to the negative 19th coulombs, okay? So he's the one that finds the charge, actually negative because he knows that they're all negative. He's the one that finds the charge on the electron and shows that charge is quantized. That means that charging must be the transfer of individual electrons, right? Because he couldn't find anything in between. Either the whole electron transferred or it didn't. So all those notions that we knew to be true way before Millikan are proven through this experiment. So why is it important? Because it proves that charge is quantized. It finds the charge on that electron. It proves that electrons are the mobile unit of charge transfer. And then because he's able to know the charge on an electron, the work that Thomson then reveals the mass of an electron. And from there, knowledge explodes. From there, Rutherford couldn't figure out what the atom looked like, really. But someone only a few years later is able to do that. You might know the work of Bohr, Niels Bohr. The Bohr model of the atom absolutely relied upon Millikan's knowledge of this, because once you know the mass of the electron and you know the charge on the electron, you can really start to talk about the structure of mass and how and why things move around in the ways that they do. You'll remember this diagram from the other day. Remember the whole notion of the Bohr model of the atom, that there were particular shells, right? Particular allowable energies that could happen. That is something that would not be possible if we didn't know the charge of what these things are and what the mass of these things are, right? This is actually a picture of the Bohr model of the atom. And so all of that becomes possible because of the work of Millikan and his compatriots.